I'll get started here. So welcome to lecture 13 of Comp 551. So as I mentioned last lecture, today we are moving on from, in some sense, the first unit of this course. So in some ways you can think of the beginning of this course was a bit of a crash course in supervised learning. It was almost, survey-like in that we were kind of jumping from method to method, making sure that you all get a foundation in terms of what are the different standard supervised machine learning algorithms that people use, things like linear regression, logistic, naive Bayes, etc. So now we are moving on to the neural network or the deep learning portion of this course. So we're going to have a lecture today on the classic neural networks, and we'll talk about this idea of what's called backpropagation. So as I'll kind of say at the beginning, today we're going to compute some nasty derivatives, but there's derivatives in this lecture, and then next lecture after this we're going to discuss what's called backpropagation or automatic differentiation, which is the idea that you actually don't need to compute derivatives anymore. All you need to do is specify a model and a loss function, and it all gets done for you. So today, in some sense, is the last day where we're going to have some nasty calculus to do, and then after that, we're just going to talk about how that calculus can be done automatically for you by things like PyTorch and TensorFlow, and then we'll discuss different types of deep learning models, so deep learning for vision, which is going to be relevant to Mini Project 3, as well as deep learning for text and a number of applications. And one thing I'll say is that I've actually added a new reference in the suggested readings where there's some textbook recommendations. For the early neural network material, there's a number of different presentations of it. But once we get into the deep learning material, there's the deep learning book, which is quite good, but there's also they're actually technical blog posts. They were written by Christopher Olah, who is a former colleague at the Montreal Institute of Learning Algorithms, and they're really, really good. So if you're looking for something that's maybe a bit more digestible than some of these textbook chapters, these blog posts by Christopher are really, really good, and I'm actually, in collaboration with him, basing lectures off of a lot of the way that he does it, so I highly recommend those. Ian Goodfellow's book, and Aaron Corville's deep learning book, also really good. So as we move on, there's a little bit of change. We're not going to be referring to Bishop and Hasty in these textbooks really as much anymore as we're transitioning to the more deep learning material. So the other thing to take stock of is where we're at in terms of Mini Project 2. I know a lot of people are busy at work on that. So the first thing I want to say is that everybody's doing quite well. So I've just shown here, this is like people like the 50s, right around 50, the groups, and these people are all getting close to 90. So I just want to make sure that people know that once you're around here, you're getting a 29 out of 30 pretty much-ish on the competition part of this, because the scoring function is a linear scoring function, right? So it doesn't matter what your rank is in the class. All that matters is kind of how close you are to my baseline, and you get 100% once you're there, and the top 3 get bonus 5 points. So I just want to say this because I feel that, people are busy, especially undergrads who are taking lots of courses. So if you're around here, you're fighting for probably half a point at most, which is half a point on an assignment that's worth 15%. So it's really a very minor part of your grade. So I would probably, again, recommend focusing on the write-up, and unless you really, really are having fun and want to try to get those bonus 5 points, if you're around 90, it's, you're doing very, very well. You're going to be around 29. And again, what's shown on the public Kaggle leaderboard is just a subset of the test set. This is to prevent people from kind of overfitting to the leaderboard. So the final numbers might change by a tiny bit, and again, that's why you probably don't want to, if you're really fighting trying to get that 0.01%, it might not be the best use of your time for this project. The other thing that I'll say is, so just to be transparent in terms of how we're going to approach grading for Mini Project 2, and also this is going to kind of carry on into Mini Project 3. So everyone's going to be doing these reports, and of course, this is not the case where it's just kind of you're right or you're wrong. We're grading these reports and kind of their quality, the quality of the overall approach. So for example, if you were, trying to maybe train on the test set, things like that, that would be a no-no. But for the most part, it's kind of a bit of a holistic evaluation in terms of how you're presenting your approach, whether or not it's coherent, whether or not it's reasonable. We're not checking off a list of did you do X, Y, Z. And as we go to mini project 3, it's going to be even more open-ended. We're not going to have you, be required to use some particular techniques. You're going to use whatever you want. So I'm just going to say here that the grading, how it's going to work, is roughly, it's going to be a scale like this, where we're going to be grading reports about whether or not they're kind of, a perfect report is a report where there's no areas for improvement. That's a very rare thing to happen. But otherwise, there's going to be outstanding reports, roughly kind of the top 10% of the class. There's going to be good reports, and there's going to be average reports. And, for the most part, people are going to fall into these categories. We hope that nobody falls into the significantly below average or serious issues. And really, what we're going to do is we're going to figure out where people fall into these categories by having multiple TAs look at assignments, trying to be as fair as we can, and we're going to give everybody strengths and also areas for improvement for their reports. So we're going to tell you what you did well or what you can improve upon, and especially for a lot of people who are following in the average bin, is going to tell you, okay, what you could do better. And the important thing is that for mini project 3, we're going to have a same kind of scale, but it's going to be relative to the baseline in mini project 2. So what this means is that if everybody who was average quality, their report in mini project 2 made their report significantly better, then the entire class will go up into the good quality bin. So this means that basically if everybody gets better from mini project 2 to mini project 3, the whole class goes up. So we're not going to kind of grade even harder on mini project 3 even though you've made improvements. So that's the goal here, is that mini project 2, the competition aspect, again, everybody in most of the class now, more than half the class is near 100% there. So it's the write-up is where we're kind of trying to make sure you're focusing your time so that we can give you good feedback for mini project 3. And mini project 3 is going to be a little bit more difficult for the actual competition. So that's just, so you guys know how things work, so there's no surprises in terms of how we're grading. And again, I want to emphasize that, we're not going to be taking off points because, oh, you didn't explicitly do this one. I mean, obviously, if you didn't implement naive Bayes, you'll lose completeness points. But there isn't, a one right way to do things. You could use k-fold cross-validation. You could use bootstrapping to get estimates of how good your models are doing. There's all kinds of things you could do. But the important thing is that it's a coherent thing to do, and that you write about it well, and that your model makes sense. So that's just a little bit on mini project 2. And the other thing I want to talk about before getting into the lecture today, so trying to just take care of some business before we move on to the neural network component of this course, is I'm actually going to go over the kind of main question in Quiz 5. Quiz 5 had some issues in the first version of it, so we extended the deadline and fixed some things. But also, I feel like this is something I'm going to try to do here and there, is actually just go over one of the more difficult questions in the quiz so that, we're actually learning and not just kind of being like, oh, I didn't do well or I got well, but I don't really understand why. So trying to just give a bit more kind of interactive feedback about the questions we're asking, especially as we're ramping up towards the midterm. So this Quiz 5 question, and which is actually relevant for the second attempt for Quiz 5, it's not exactly the same, but if you're paying attention here, it'd be very useful if you're going to try the next version of the quiz, which is out now. So what we're looking at is we're looking at a data set where our data follows a logical AND function. So we have that the points are negative down here. Any one where one of the points is -1, then this is a negative point. So -1, 1 is negative, -1, -1 is a negative point, and 1, -1 is a negative point. So it's like we're thinking of -1 as being false and 1 as being true, and this is basically a logical AND function. And our goal is to try to figure out what the parameters of a hard SVM would be on this data set. And the hard SVM we're going to look at is this one here, where again the prediction we're making is we're taking the dot product between our learned weights and our inputs. So these are our inputs. And we're also going to have some bias term. So it's actually important that we put this bias term in here. The treatment of the bias term was maybe a little fast and loose in previous lectures, but it's much easier to learn things in the SVM context if we just write things out like this, where we have our bias term as a separate thing we're taking out. Okay, so what this question really entails is trying to figure out what the decision boundary of a hard SVM on this logical AND data would be. Now, you could just solve the convex optimization problem that we put up in the slides and run this through a solver, and that would be a perfectly reasonable way to do it, but what we were hoping is that, approach this in a slightly more maybe kind of just intuitive way. And in fact, there are some ways that you could solve this with linear algebra knowledge. The way that I solve it is kind of just with an intuitive guess and check approach. But what you can notice is that, well, quite obviously we have these three negative points, and our decision boundary is going to be somewhere in between these points and our one positive point here. And in fact, if we're looking at this and if we're kind of remembering that the whole idea with this SVM is we're trying to have the maximum margin. We want to have the decision boundary so that it is as far away from all the points as it can be. Well, because this is a very simple symmetric data set, what that means is that the line that we're really looking for is the line that's equidistant between these 3 points. So you could solve that in just a linear algebra, using knowledge from linear algebra. Another thing you can do is you can look at this and just reason a little bit and think, well, a reasonable line is going to be the line that goes through 0, 1, and 1, 0. And we can use our knowledge of basic linear algebra to figure out what would be the equation for that line. So again, this is this line that goes through 1, 0, and 0, 1. We can solve for the classic slope-intercept form of that. So this is like y equals mx plus b, but we have x1 or x2 and x1 instead of x and y there. But an important thing to note is that when we're representing the decision boundary in the SVMs, the way we're representing this W vector is in normal form. We talked about W as specifying the normal line, the perpendicular line to the decision boundary. So this is not in this slope-intercept form. It's in what's called the normal form, where we're representing it like this. We're moving everything over to the left side. So we have x1 plus x2 minus 1 equals 0. Or if we want to represent it in kind of the parameters, we have that our weight vector is 1, 1, and our bias term is negative 1. So basically, the intuition here is we can reason about the fact that we want a line that is equidistant between these 3 points. We can reason that the reasonable line to look at here is the one that goes through 1, 0, and then 0, 1. And then we can use linear algebra to solve for this line. And again, remembering that in the SVM world, our parameters are really specifying the normal. So we have to put the equation of the line in normal form, not in slope-intercept form. Yep. Yeah, so that's a good point, actually, because, I mean, it's generally you're going to be, so it's multiplying it by a constant, and that's still going to be okay, because you're going to have, in that case, we're going to have that negative sign over here and then a positive sign there. Yeah, I think that you're correct, but that would be, I'll have to think about it. If that's the case, then I'll give back some points on the quiz. That's a good point. That -1, -1 would also be reasonable, but it does, yeah, it does. So, like, I have to double check because that shouldn't, like, it should be 1, 1, but I don't want to say something incorrect now, and I will give people more points if -1, -1 is correct, but my intuition is that that's going to cause a little bit of an issue in terms of the signs and everything working out. But great question. If we had -1, -1? You mean the line would be over here? Yeah, but you can also just do that by fiddling with the bias term. So there's a little bit of, you have an extra degree of freedom here, which is, I guess, one of the things that in the revised version of the quiz, I do specify what you should have for B, which does get rid of that ambiguity, but it's a good point. I will get back to you on that, and also get back to you on that issue of, because we shouldn't, generally you can often multiply decision boundaries by a constant factor, but that usually shouldn't be allowed. But I will, yes, it's a really good question, and I will get back to us on that. Okay. So what we can note is that this thing definitely classifies everything correctly. That's nice. Then we can also calculate the distance between these 3 points and this line. And there's various ways to calculate this distance. There's a formula you can get from basic linear algebra, for example, and we can figure out that these 3 points are all square root of 1/2 away from this line, so that's good. So the distances are all the same, and this is kind of a certificate of optimality for us. I mean, we could go about this in different ways. You could also just solve for the line that's equidistant from all of these, but what we did is kind of used intuition, computed these distances, and say, okay, they're all square root of 1/2 away, so that's good. And this means that this must be the optimal line in some sense, because if we tried to move this line at all, it would be closer to one of these points, so it would be a smaller margin. So we kind of know, because we're bounded by this triangle of points, this is kind of the best that we can do. But then there's also a minor ambiguity that comes up in terms of, well, what is the size of the margin here? So we said that the distance of these points, each of these points is the distance of 1 over square root of 2 from this line. And so is the margin equal to just this distance or 2 times this distance? So in lecture, we said 2 times this distance, and also in some of our diagrams we had 2 times the distance, but we also sometimes just called this the margin, just the distance between the nearest point and the boundary. And this is unfortunately somewhat of an ambiguity that goes beyond just the lecture slides, but in fact is different conventions. For example, the Bishop book disagrees with Wikipedia, so we will always be unambiguous, tell you, we'll either accept both answers or we'll tell you which one. Really, it's a constant factor of 2. There isn't one that's necessarily right or wrong, it's just a convention. In the quiz, I originally used the case where we just look at this distance, so we don't multiply it by 2, because in my opinion what's kind of nice about that way is that if we look at this optimization equation that we derived for the hard SVM, then according to this exact optimization equation, we don't multiply by this extra factor of 2. Again, it's all just kind of 6 and 2 3s, because the margin is really defined by this 1 over square root of 2, and we can multiply this by 2 or not. And again, we'll always accept both of these answers from now on, or really be clear about what one we want. But I just want to bring that up because it's a bit confusing. In the lecture slides, we say one thing. The Bishop book actually uses a slightly different definition. It's just a factor of 2, and one of those places where, frankly, just a convention. But an important convention to know, because if you're, say, reporting margins in a paper, you should probably be unambiguous about which version you're using. So are there any questions on that? There's a great question about the -1, -1. I will look into that. But otherwise, any questions on this material before we move on? All right. Awesome. So now we're actually going to move into the content for today. And there's going to be 2 motivations for the content we're looking at today. So the first one is this idea of stacking. So in our last lecture, we were discussing these different ensemble methods. And the ensemble method we talked about at the end was this idea of stacking, where what we did is that we trained a bunch of models, and then we took the output of these models, and then trained another model on the output of these models. So we tried to build a more complicated model by taking the output of some simple models and then training another classifier on the output of those models. This is a very powerful idea because this allows us to take even some simple models and we can stack them and make more and more complicated models. And so today when we're talking about neural networks, we're really going to take this idea of stacking to the extreme. The other thing we're going to build on top of is the idea of the perceptron, or in some sense a very simple linear classifier or linear predictor. So this is related to our discussion of the hard SVM, but again, the perceptron is this really simple method where all we're doing is we're classifying something as on the positive class if the sign of the dot product between the features and the parameters is greater than 1, and negative otherwise. So it's like an SVM, but we're not worrying about margins or anything. It's just a really simple linear decision boundary. Now, the decision surface of a perceptron is a linear decision boundary. Remember, the perceptron is able to separate or correctly classify any data set that is linearly separable, but it can really only handle linearly separable data. The perceptron is just trying to figure out some line or some hyperplane that separates the positive and negative classes. So what this means is that this model can do quite well on a data set like the one on the left that is linearly separable, but it just can't handle data that is not linearly separable. So what is the canonical data set or type of data that's not linearly separable? Well, people really like to talk about what's called the XOR function. Why the XOR function is kind of the simplest function that you can't represent with a linear decision boundary. So the XOR is just the logical function where we have negative if both the points are false or both the points are true, and positive otherwise. And unfortunately, there's no way to linearly separate this data. Even though it's a really simple Boolean function, this data is not linearly separable. So this is an issue. And previously, we've talked about trying to do feature transformations, trying to do all kinds of things to increase the complexity of our models. But now we're going to take the stacking idea and, again, take it to the extreme, and we're going to say, well, maybe the right thing to do, instead of trying to come up with different features for our data, maybe we can handle these nonlinear boundaries just by stacking multiple perceptron-like things together. And these stacks of perceptrons, or perceptron-like elements, because they're not just perceptrons, these are the traditional notion of what a neural network is. So in a neural network, every unit, every neuron in a neural network is like a little perceptron. And we're stacking, we're combining a bunch of these perceptrons together to make more complicated decision boundaries. So to give you a concrete example of how this can actually work, so say we have this XOR data set. Unfortunately, not linearly separable. So this is the data set on the left. But suppose that we run 2 perceptrons on this data. So we run perceptron 1, which we call the neuron or net1, and it learns this decision boundary. Now this is a reasonable decision boundary. I mean, it's going to correctly classify 1 of the points, but or 3 of the points and get 1 wrong, but that's the best it can do. And suppose we run another one, and it again learns a reasonable decision boundary. This data is not linearly separable, so the perceptron algorithm is just going to kind of oscillate until we make it converge by lowering the learning rate, but it'll figure out something, and in general, it's going to come to solutions, and quite possibly we'll end up with 2 perceptrons that learn these 2 different decision boundaries. So neither of these decision boundaries is actually capable of representing this class distribution, right? We're getting an error of 1 for both of these networks. So network 2 is saying, okay, this one's negative, these ones are positive. Network 1 is saying this side is positive and this side's negative. But what if we stack? So what if we take these original perceptrons and now we take their output and then we stack another perceptron-like thing on top? So what if we make a new space where now the axes of this space are the outputs of these perceptrons? Well, what this is going to mean is that for these 2, the 2 positive points, well, both of them are classified as positive. They're classified correctly by these 2 networks. But if we look at this negative point up here, so it's classified as being positive by n1, but negative by n2. And then we have this other point down here, which is again being classified as being negative by n1 and negative by n2. And now we put this data in a new space, where a new space is the output of our original perceptrons, and in this new space it's linearly separable. So we had a data set that was not linearly separable, but we were able to separate this data by taking two perceptrons and then making a stack on top of these two. So by stacking, in total we have 3 perceptrons. Now, one issue with perceptrons is that they're kind of numerically hard to deal with, yeah? There might have been yes, there might have been one of those should actually be up, I think. Yeah, you're right. I'll fix that before I repost the slides. Oh, sorry, so the question was just, I think that there was one of these should actually be up here. This was an error. So it'll just, it's still linearly separable, but it just was, this one's actually classified as being positive by n2. Yes. Yeah, great point. But yes, so this is a reasonable idea, supposing that we actually write down our axes correctly when we make our animations. These things can work, and they're a reasonable thing to do. Again, this is another way of looking at, in this course, we've had a bunch of different ways of trying to make our models more complicated. We first had these ideas of trying to transform the features. That was a reasonable thing to do. We had some more complicated models. We talked about ensembling. And now we're doing something similar to ensembling, but it's really this idea of stacking, and really this idea of we can get complexity through depth, through iteratively applying a bunch of simple classifiers. Now, the perceptron is an appealing thing to use because it's so simple. It's, again, in some sense, the simplest linear classifier we could have. It's just trying to figure out a boundary, and that's all. So that's nice. But the issue with the perceptron is that it's mathematically annoying to deal with because it's not nicely differentiable. So when we actually want to build these complicated stacks of simple classifiers, we're not going to use the perceptron as our base element. We're actually going to use something that's more similar to the logistic. And in fact, what we're going to do is we're going to take the output, and instead of using this sign function, this hard decision that the perceptron uses, we're going to use this sigmoid function. So it's shown up here. I'll use it a little small. But this is this simple logistic, this function we've seen a bunch of times now, where this logistic function is this function where we feed in a real valued input, and it squashes that input into something between 0 and 1. So it takes an unbounded continuous input and outputs a probability. So instead of us doing this hard perceptron threshold, we're instead feeding it through this logistic or sigmoid function. And again, an unfortunate place where there is not consistent terminology. People call this a sigmoid in the context of neural networks, but it's often called a logistic function by statisticians. So I'll try to call it a sigmoid most of the time now. That's what it's called in neural network literature. But again, just to be aware, this function up here is often called logistic or sigmoid. And if we recall, this function was nice. One, because it takes a continuous input, and it takes our kind of rough continuous decision boundary and turns that into a probability, so that's nice. It's differentiable, so that's nice. But it's not just differentiable, it also has this really nice identity for when we're taking the derivative of the sigmoid applied to something, so of sigmoid of z with respect to z, we get this nice identity where it's just the sigmoid of that input times 1 minus the sigmoid of that input. So the sigmoid function, it's nice because it turns real valued things into probabilities. It kind of squashes things into the 0, 1. It's nice and smooth, nice and differentiable, and has this nice identity for the derivative. Okay, so this brings us to the most basic feed-forward neural network. So what is a feed-forward neural network? Often called an FNNN, also called a multi-layer perceptron, despite the fact that we actually use sigmoid units. You'll often heard these things called multi-layer perceptrons or MLPs. So what these feed-forward neural networks are is they are a stack of simple sigmoid classifiers. So basically what we're doing is we're stacking a bunch of simple logistic models. So what we're going to look at here is this diagram, and we'll see this diagram many times in this lecture. And what this diagram denotes is it means that we have first what we call our input layer, and these are sometimes called the input nodes or input neurons. I don't really like calling these things neurons because they're not really connected to biological neurons. Some people call them nodes. I think they're really just vectors, but people can call them what they like, whatever seems reasonable to them. But importantly, we have our input. So this input is, we have a three-dimensional input space, so we have three features. And then what this is denoting is we're saying that these features are all being fed to make a prediction to generate this hidden unit. So this hidden unit is just a logistic, it's a sigmoid function. So we're taking the dot product of a feature vector times the inputs plus some bias term, and this is giving us our hidden activation. So this is basically just like this stack of perceptrons we talked about, but again, we're just stacking sigmoid or logistic units. So we have our input x. To get h1, we're doing w1 times x plus b1 to get h2, and then feeding it through sigmoid, and then we're doing an analogous thing down here, and then we can do another function. Now we have what's in our classic stacking, like our meta model, we can use to then make a prediction based on these hidden units. So we took our initial data, we mapped this initial data to some hidden activations, some hidden nodes, and then we predicted our output. And this is basically the same thing we were doing with stacking. These hidden units are just the predictions made by the initial models. But again, in the terminology of neural networks, we don't call these things the output of the base models, we call them the hidden units or the hidden activations. So again, just going over this, what are the things we have to look at here? Well, first off, we have our input data. This is just our X data, and for pretty much the entirety of this lecture, we're just going to be talking about the case where we have one data point. We're not going to worry about the whole training set. We're just dealing with how do we do the computation on a single input data point X. So this represents X. X is a three-dimensional feature space. Now our hidden units are a linear function of X, and then plus a sigmoid applied. And one thing I'll just point out here, and this is going to become important not so much in this lecture, but more important as we get to more complicated variants of neural networks and deep learning, is that the easiest way to represent this is in matrix notation. So the easiest way to represent this is that we have our input data X, we have our hidden units, which are just a vector of h's, and this vector of h's can be computed as the sigmoid times a matrix times X plus a bias vector, where this matrix is just the stack of these two different parameter vectors. So basically, instead of thinking of us having our input and then two different models being applied to the input, we can really think of this as just where it's basically the same model. They're both linear logistic models. So it's basically just we have a two-dimensional output or a two-dimensional version of a logistic as this step. And again, it's not super important, but it's important just because it can get pretty annoying. There's going to be a lot of indices and a lot of notation, a lot of things to keep track of, and the matrix notation for a lot of these neural network and deep learning models is a lot easier to deal with, where we're thinking of our hidden layer, our hidden units, just as a vector of what are sometimes called activations. And then finally, based on our hidden input, we have our activation, or our output. And our output is going to be, depending on the task, this output, what we apply to get our output, so we take our h's here, and then we feed them through a linear function. Sorry, that should actually be h. I apologize for the typo. So we're applying the wt times our h here, that should be h, and then we're going to feed this through some what we call an activation function. So if we're doing classification, like binary classification, this would be a sigmoid because we want to have something that's going to be a probability for the binary classification. If we're just doing linear regression, we actually just have the identity function here because because they're just predicting a continuous value. But really, what we use at the final layer is determined by what our task is. If our task is predicting something real valued, well then we can just use a linear function or an identity function here, and this is just a linear model. We could do classification with a sigmoid, etc. And in terms of how can things get more complex, well, we can have different numbers of hidden units. Yeah. This is a great question. So the question is here, so if we're using the same sigmoid function to compute h1 and h2, why are they doing anything different? Well, the important thing is the sigmoid's the same, but these w vectors are different. And so you might wonder, like, why are these w vectors learning anything different? And this is, again, I guess, the important difference between a neural network and a basic stacking. So if we were doing basic stacking, we would train the kind of hidden unit 1 and train the hidden unit 2 independently and then take their output, and then they probably would just do the same thing. But what we're going to do with the neural network is we're going to train this whole thing together. And in doing that, these units are actually incentivized to learn different things, because if they just learn to output the same thing, if they just learn to have the same w vectors, then the model's not going to perform that well. So basically the important difference, probably the most important difference between a neural network, which is like a stack of perceptrons or a stack of logistic functions, but the important difference is that we're not training these sequentially, we're actually doing the training of this using gradient descent all jointly. So these things can learn to kind of act in concert together. It's a really important point. Yeah? No, this is also a really great point, and I think, yes, so I was showing this. So, and the other question is that, well, what are the constraints in terms of the dimensionalities? Well, for one, there really isn't a constraint. Generally, people make these things smaller, so the hidden dimensions get smaller, but there can be reasons to have the hidden dimensions actually get bigger. And there's some cases I've done research where that's actually necessary to make the models work. And the other important thing is that we're not limited to just one hidden layer. We can have as many hidden layers as we want. Yeah. Variable. Learnable. Yes. So can you make the number of hidden layers learnable? Yes, although that is a relatively difficult and advanced way to try to do things. So it's pretty popular right now under the name of what's called neural architecture search. And you can try to learn this. Why is it difficult? Well, basically, now you're trying to make this decision of how many hidden units I have, how many layers I have, and that's a discrete decision. And we don't like discrete decisions because they're hard to run gradient descent on. So it's really difficult to kind of directly optimize that. So yes, you can learn the architecture in addition to the parameters, but it's really tricky to do, and it's something that only in the last couple years, with a lot of compute power, have Google and OpenAI have had some positive results in this space. Yeah, it's a great point, though. Yeah. Yes. Yeah, so the question is, at the end, kind of what do we know? How much of this, like, is this red part like a black box to us? No. So what we'll learn during learning, what we'll talk about today, is that we're going to learn these W's, so we're obviously going to know them. These are what we're going to be optimizing using gradient descent, is what are the weight vectors at each layer. But also, when you run what's called the forward pass, you can explicitly look at what the activations are in each of the hidden layers. So we kind of have full access to everything internally within this model. Yes, good question. So then why are they called hidden? Yes, this is another place where, frankly, it's maybe not the best terminology. They're called hidden because of their relationship to what are called hidden or latent variables in probabilistic modeling. So those variables they're hidden in the sense that they're not directly related to the input and output, but they're not hidden from the modeler. Great question. So is there any kind of rule for deciding how many hidden layers we need to have? Here, there is no hard and fast rule, and in fact, it's going to take us a little bit to really kind of discuss the intuitions of when they should be really deep and not deep. I think that the models we're talking about today, which is what's called the kind of the most basic, simple feed-forward neural network, these are usually only a couple layers. And as I'll discuss, with 2 layers, so with 2 hidden layers, you can approximate any function, any continuous function. So in principle, 2 hidden layers is pretty much enough. But in general, how deep should we make these things is a modeling question, which you can use things like cross-validation for. But when we get into the more advanced versions of deep learning, where we're explicitly talking about deep learning for vision or for text or for other problems, I will give us concrete insights about how deep things should be and what the current practice is. So for example, in vision, the state-of-the-art models right now are extremely deep, like hundreds of layers. But there's particular ways that they build the models so they work well with that. But for the models we'll talk about today, the simple feed-forward neural network, these things are often modules or components that people use in a lot of deep learning applications, and generally they're 2 layers is the standard. Yeah, so the question is, so neural networks kind of have this conceptual connection to stacking. So is it weird, or would it be sensible to use neural networks in a stacking ensemble? I would say that yeah, because in my opinion, if you're going to use neural networks in a stacking ensemble, why not just basically make it a 1-layer deeper neural network, and you can train the whole thing jointly? Again, that's the difference between stacking and neural networks, is stacking, we're kind of independently training a bunch of things, getting their output, then training a meta model, where here we're training all the layers jointly. So yeah, to me, I personally would say that it wouldn't seem that reasonable to use stacking with a neural network, but say you had a neural network and you also had a bunch of 1 nearest neighbor models and a bunch of things, and you want to ensemble all of those, it would be perfectly reasonable to use stacking. So I think stacking with just neural networks as the base model seems kind of weird, but if you have neural networks and a bunch of other models, then it's a perfectly sensible thing to do. Yeah. Yeah. It's a good question. So the question is, so there's really, now we've introduced 2 degrees of freedom in terms of how we can add more complexity to our model. And it's interesting, just as a note, right, this is going to be something that's, a little bit strange in terms of, for the initial part of this course, a lot of what we talked about was how to, regularize, how to reduce the number of features, how to make our model less prone to overfitting. And now when we get to deep learning and neural networks, it's all about making really deep, complicated models where we can add all these hidden units. So that's one thing to keep in mind, is that first off, we should maybe be a little bit wary about how much these things are going to overfit. But if we wanted to make these things really complicated and increase their complexity, so the kind of complexity of the functions they can represent, so you could increase the size of these layers, or you could increase the depth. This is, again, another place where there's really no hard and fast rule. Generally, increasing the depth will increase the complexity more than increasing the size of one of the individual layers. But it's really, that's just kind of a heuristic that if you increased the number of units by 1 or added a whole other layer, adding a whole other layer is going to add more complexity for the most part. But again, unfortunately, this is a place where kind of cross-validation is your best friend, but not just cross-validation. I think I want to emphasize that the neural networks I'm talking about today, and to some extent tomorrow, are really simple neural networks that aren't used too much in practice. When it comes to using these neural networks in practice, there's going to be kind of domain knowledge that we use of, like, what are the right depths and sizes for image data or for speech data. And I will try to give us concrete insights on that. So it's not all is lost, like it's a complete Wild West in how we should figure out the architectures for our neural networks. We have many years of great research to build on top of, but unfortunately it's going to take us a few lectures to get to the point where we can talk about the kind of current practice that people use. All right, cool. So as a quick note, why are these called feed-forward neural networks? Well, first off, they're called neural networks because a long time ago people thought these were kind of like the way that neurons work in the brain. They're called feed-forward because the information is going from the input layer to the next layer to the next layer. The information's always flowing in one direction. So there's no cross connections within an individual layer, which would be kind of weird. And there's also no backward or recurrent connections. So when we're computing, so I think it's useful now, and it's going to come up again, to think about the flow of data in what we sometimes call, in kind of more modern deep learning, what's called the computation graph. And that we'll talk about explicitly tomorrow, right? This graph, this diagram we have here is telling us that we have our input data, we're sending it, doing some transformations, and then we have some new data here. And then we're sending it and doing some transformations, and we have some new data here. So the structure of this diagram is telling us the flow of the data and what we often call the compute graph. So they're called feed-forward neural networks because this data is flowing forward. We're taking the input data, transforming it a number of times to get the output data. Yeah? Yeah. Yeah, so why this feed-forward model? Well, first off, we will discuss what's called recurrent neural networks in 4-ish lectures, depending on how things go. Depending on kind of convolutional neural networks will come first. So, no, it is very reasonable, and in the early days of neural networks, people explored with all kinds of interesting things. So, why is this the canonical? Like, why not aren't kind of ones with recurrent connections something we use more often? The short answer is that it's really hard to take derivatives when you add these sorts of strange connections. So if our data flows, if our data has a kind of cycle dependency in it, in the flow of this computation graph, and we want to compute a derivative, we actually end up with the derivative of a one parameter depending on itself. And you can get infinite dependencies. So there's ways to solve that, and that's what recurrent neural networks do, is they get around this. But yeah, the reason why we have all the information flowing forward and don't do crazier things is because we really need these things to be tractable to train. And also just frankly, those crazy things generally don't work that well. But there have been, there's a lot of really interesting, and for the most part, research that took place in like the 80s. Really interesting crazy neural networks where they solved them all by hand before people had automatic differentiation. So these days, it's more boring and more complicated in different ways. All right. So, and the other thing to note is that we call this a fully connected feed-forward neural network. And what do we mean by fully connected? Well, I just mean that we have arrows between every node at layer 1 sends information to every node of the next layer. So we call this a fully connected network. So almost always the networks we deal with will be fully connected, even when we're talking about recurrent neural networks or convolutional neural networks. In some sense, they're usually in this kind of fully connected style. But you can, if you want, introduce kind of more structure into your neural network. So you could say that hidden unit 1 only gets information from the first feature. And what this would mean is that you're constraining the weight vector of the linear function that generates h1. You're constraining this weight vector to have zeros in the second 2 entries. So you could do this, and again, this was kind of specifying the architectures of these neural networks in this way was a relatively popular thing in the very early days of neural networks. But now, practically speaking, I haven't seen a feed-forward neural network that was not fully connected in many years in a research paper. So just kind of, we call them fully connected feed-forward neural networks, but they're just the standard neural network that people use these days. Okay. So what do we do? Just to reiterate how we'd actually compute, so kind of more, not in a diagram, but in kind of actual pseudocode. What is it that we're computing? So what we call the forward pass is when we take the input, so we have one example, x, and we feed this through the neural network. We call this the forward pass. This is basically generating the prediction of the model, and we call this the forward pass. So the easiest way to write down this forward pass is like this, is that the first thing we do is we just, for notation's sake, we say that H0, so the 0 layer hidden units, are equal to the inputs, and then the hidden units at layer I are a sigmoid where we have our matrix times the hidden units at the last layer plus a bias term. So it's a really simple kind of iterative or recursion that we're doing here, right? Where to get the hidden units at layer I, they're a sigmoid times a linear function of the hidden units at the previous layer. And then once we get down to the final layer, so once we've done all of our layers, H, then we get our output, our final prediction, by again doing a linear function of the final hidden layer and then feeding it through some activation function. So, and again, in the simplest case of regression, this activation function is just the identity, because we're just taking our hidden units, and then our final prediction is just linear regression on these hidden units. Yep. So you're going to learn these biases. Generally, you're going to initialize everything to small random numbers. And so the biases, so yes, in some sense, we're adding this bias at every layer. But the important thing, I think, to note is that this sigmoid is always squeezing us back down to 0, 1. So an issue we're going to talk about in future lectures is what's called kind of like vanishing and exploding gradients, or vanishing and exploding forward passes. So if your parameters aren't set well, things can blow up. You know, if you keep iterating this, your things can go crazy. So you have to be careful, but generally the bias term is going to just be learned to be quite a small value. But it's a good point. So now, how do we actually learn these things? So what we're going to assume is that the network structure, so we kind of know how many hidden layers we have, etc. And our goal is to find weights for all of the functions and all of the layers. So remember, every layer has this weight vector, or so this weight matrix that we're trying to learn. So there's one vector for every unit in our hidden layer, so shown here. What we're trying to learn is these parameter vectors, as well as our output parameter vector, and we also want to learn these bias terms. And we're going to do this using gradient descent. Now, why are we using gradient descent? When we did some other models, we had some nice closed form. Unfortunately, now for these neural networks, they're so general and they can be so complicated that it's just impossible to actually come up with the closed form solution. But what's nice is that we're using a bunch of differentiable, and we have this sigmoid function that has this nice derivative or identity for its derivative. So we're just going to run gradient descent. So what we're going to do for an example here is we're going to take regression as a simple case. So the y values, the thing we're trying to predict, is just a one-dimensional continuous value. So our output layer is just a linear function. And what we're going to think about is how can we change the weights in this neural network based on a single training example, assuming that we're using a squared loss. So our loss is 1/2 times the square difference between our prediction and what the actual value was. So again, this is like the gradient descent we were doing before, but we're not looking at the entire training set. We're just doing gradient descent for a single example. So first, we're going to try to do gradient descent for the output node. And like I said, it's maybe not the last time, but this is the last time for the next few lectures where we're going to actually have to do this gradient descent by hand. Tomorrow, or next lecture, we'll talk about how the backpropagation or automatic differentiation solvers do it for us. But it's good to know that people did this by hand for a long time. So how do we do it? Well, what we're trying to do for the output node is we want to know what is the derivative of the error with respect to our output weights, these W subscript out. So the first thing we're going to do is we're going to apply the chain rule. And really, training neural networks and deep learning is really just smart application of the chain rule over and over again. So we apply the chain rule. So now we have separating out to the derivative of the error with respect to our prediction, the derivative of our prediction with respect to our parameters. Now, the derivative of the error with respect to our prediction is pretty easy because this is just, 1/2 and this is the square difference, so that's nice. This is just our error. Now, when we're trying to figure out what is the derivative of our prediction with respect to our parameters, well, here we just have a linear model. And what you might notice is, in fact, this is just the same, basically, as gradient descent for linear regression, off by a couple constants. And at the end of the day, so we're taking the derivative of this linear function with respect to this parameter here. And at the end of the day, what we end up with is that our gradient for the output with respect to the gradient of our error with respect to our output node is basically just the error, so the difference between what we should have predicted, what we predicted and what we should have predicted, which we call the delta out, times the hidden weight, so times the input at this node. So that's not so bad. That's actually just pretty much the same as just the derivative for linear regression. But now, what if we want to calculate the derivative of our weight vectors at one of our hidden nodes? So something that's actually inside of our network. It was easy at the final node. It was basically just like linear regression. But what if we want to determine the derivative of the error with respect to the weights of the hidden node? Well, again, we're going to apply the chain rule. And now we're going to, first off, note that the derivative of the error with respect to the prediction is this thing that we call delta out in the last slide. This is basically just how wrong we were at the output node. So our gradient at the hidden node is kind of some function. It's some multiplication of our error at the output node. So we already computed that error. We're fine. Now we can apply the chain rule again. And now what we're looking at is what is the derivative of our prediction with respect to this hidden node, this hidden output, and how does this hidden node, this hidden output, depend on the parameters that we're learning. And again, here, recall that this hidden output, hi, is just a logistic or a sigmoid function of our inputs, right? This is just a linear in here, and then we have this sigmoid on top. So again, this is basically just, up until this point, we're applying the chain rule, but then what we end up with down here is very, very close to gradient descent for logistic regression. We're just kind of doing this within a slightly more complicated setting. So, based on this fact, we can get that the derivative of the prediction with respect to our hidden unit is going to just depend on one of the output weights. So again, the hidden unit is just, say, h1 here, and h1 is being dot product with the first index of w out. So that's what we have here. And then we end up finally with this, what is the derivative, the partial derivative of our hidden output node with respect to our weights at the hidden node. And this is just the same as doing the derivative for logistic regression. So it's a bit of a pain. We applied the chain rule a few times. It's maybe not the most intuitive thing to look at. And often how we write this thing at the end is we say, okay, we just have another error signal at our hidden node. And what this error signal at our hidden node is what we have the error that we had at the output node. And then we're multiplying this by the weight between this hidden node and the output node. So this is basically saying how much of the error at the output is this hidden node responsible for. And then this term here is just this term from this logistic function identity, where the derivative of the logistic function is logistic times 1 minus the logistic. And then we have our input here. So I think the most useful thing to look at here is that we have kind of our error at the output, and then we're trying to figure out how much is this hidden node responsible for that error at the output. And then we have some more kind of derivative bookkeeping down here. So it's important to understand that we're applying the chain rule is a little bit of vector calculus, but you could do this actually without actually doing any vectors. You could do this individually for each of the, not just the vectors W, but actually each of the individual entries in this vector. You're going to come to the same solution, but it's important to note that all we're doing when we're training these things, all the magic that's going to happen in the next few lectures when we start talking about automated differentiation and the fact that we can design deep neural networks with thousands of layers and all kinds of weird, crazy connections and different activation functions. At the end of the day, you could, by hand, figure out how to train that model just by cranking through the chain rule and a bunch of derivative identities. So suppose we've done this and we've figured out, we've taken all these derivatives. Now we know what the derivative is of the derivative of the error, of the error with respect to the weights of the output and also the weights of all of our hidden nodes. So how do we actually train a model in this setting? Well, this is back to our standard gradient descent, but here we're calling it stochastic gradient descent, again, because we're just looking at a single training example. We're not looking at the entire training set and computing the gradients. The way our algorithm is going to work is, first off, we're going to initialize all of our weights to small random numbers, and then we're going to repeat the following until we converge, until we hit some stopping criterion. Yep. Yes. Yeah, it actually does. So I think you're bringing up, the question or comment is that when we're looking at the derivative of, we're looking at the error, the derivative of the error with respect to the hidden node weights, this intuitively is in some sense saying, well, what is the error at the output node and how is that error related to, like, how much is this hidden node responsible for that error? But in general, especially when you get to deeper networks, you're going to have really complicated pathways where these dependencies can go all over the place, and it can get pretty, complicated to actually try to pin down, like, okay, the error at this point is due to how much it influenced this node and so on. This is very much true. So in fact, you do have quite complicated dependencies once we get to especially deeper networks, because in some sense, if we have a 3-layer network, well then the influence of this hidden node on the output can depend on its influence on all of the intermediate nodes. And that can get very complicated when you're trying to compute these derivatives and trying to do the chain rule. And what we're going to talk about next lecture is there's actually kind of like a clever dynamic programming way to do this really efficiently, where you don't need to actually sum over all these paths in a silly way. So it's very much the correct intuition that indeed the flow of the errors. So the reason why it's often called backpropagation is because in the forward pass, we're generating the prediction, and then it's what's called the backward pass. We're backpropagating the error. So we made some mistake, and then we're kind of propagating how much each unit in the neural network was responsible for this mistake. But that propagation, doing it naively, can require kind of summing over all possible paths between all nodes in the network. But we're going to do something more smart in the next lecture. It's a great question, though. So the core algorithm that's going to run the show for the next month-ish is this stochastic gradient descent algorithm. This is gradient descent, but we're doing things in a slightly different, almost simpler way. So again, what we're going to do, we're going to initialize all the weights in our neural network. It's called the initialization step. And then we're going to repeat this loop until we converge, so we have some stopping criterion. So what we do is we pick a training example, say we randomly choose a training example. We put this through our neural network. This is the forward pass, so we're making the predictions on this input x. And now we have some error, and we're going to compute the derivative of the error with respect to all of the weights in our network. We call this the backpropagation step. So we made some error, and we're propagating responsibility for this error to all the nodes in the network. We get our derivatives, and then we update our network weights using these derivatives. So this is the standard gradient descent. Again, we're updating by taking our parameter, it equals our new parameter equals the previous one minus our learning rate times the derivative. And the only difference here between what we did in the previous version of gradient descent is this idea that we're looping and looking at individual training examples. And this is actually somewhat of an important point. So we have different choices in how we organize the training data. So what I just described was what's called stochastic gradient descent. So when we're training our neural network, we're computing the error on a single example at a time. So we're just choosing one random training example, trying to make the prediction on that example, and updating our weights with the gradient update rule. You could also do something that's called batch gradient descent. That's what we've been doing in this course so far. That's what you implemented in Mini Project 1. Here we're computing the error on the entire training set and then doing our updates after doing that. There's also a middle ground, which is called mini batch gradient descent, which is we choose a small number of training examples, usually somewhere between 64 and 256, because people like powers of 2, and we're going to compute the error on this small subset of data, and then we're going to update our weights based on this error, and we're going to keep doing that. And in fact, this mini batch gradient descent is what everybody in modern deep learning and modern neural network research uses. So this batch gradient descent is just too slow to feed the entire data set through every single time, ends up being not worth it. This stochastic gradient descent, just looking at one training example every time and only making corrections based on a single training example, that tends to be very slow at converging. So the middle ground here of what's called mini batch gradient descent is very important. And the size of the mini batch, so how many examples we're using to make the corrections every time, that's actually a pretty important hyperparameter you have to set, so like the learning rate. So this is the basic neural network. Yep. Which is more memory efficient? Great question. So which of these, so the most memory efficient is stochastic gradient descent. In the extreme case where we can't fit our training data on main memory, where our training data has to live, say, on the hard drive, we could still run stochastic gradient descent every time, just reading a single training example from the hard drive, updating our weights based on the error on that example, and then loading the next one from the hard drive. So the memory footprint of stochastic gradient descent in that sense is kind of constant, so that's nice. The full batch gradient descent requires loading the entire training set into main memory at one time, basically. I mean, you could do it incrementally, but then that would kind of defeat the purpose. So generally, stochastic gradient descent is much more memory efficient. But then the reality is that what people really like to use these days for research in this area is GPUs, not CPUs, because as will be kind of obvious now, we're doing a lot of matrix multiplications, really neural networks, when we stack a bunch of them with a bunch of matrix multiplications, and then these sigmoid or other activation functions. And GPUs are really good at this. And GPUs, when you want to be most memory efficient, the best thing is mini batching, because in GPUs really like to do like a kind of batch of matrix multiplications all together. They can't fit the entire training data set in the GPU memory, but you want to have a big enough mini batch so that you're fully utilizing the GPU. So in practice, mini batching is actually the most efficient in terms of raw memory efficiency. Stochastic gradient descent is, but you're kind of wasting, you're kind of wasting power if you're only ever looking at one example every time. Cool. So in the last few minutes of this lecture, I just want to talk a little bit about the expressiveness of neural networks. And so the intention of this lecture was really just to, again, introduce this very basic neural network. We did a little bit of, calculating derivatives by hand, and then next lecture we'll talk about actually kind of the recipe for having, all we do is we specify the forward pass. All we do is we specify the model, and then we feed it to something called an automated differentiation engine, and it solves the learning problem for us. But first, before we get there, it's worthwhile talking about why neural networks are such a powerful thing and why they're kind of the approach that is now the de facto standard that people are building on top of in machine learning. And a lot of that has to do with the fact that neural networks are extremely expressive in kind of a universal way. So if we think first of a neural network with no hidden layers, well, then we basically just have a perceptron or logistic regression. So it can handle linear data. A neural network with a single hidden layer, that can represent every Boolean function, although it might require a number of hidden units that's exponential in the size of the input data. And every bounded continuous function can be represented or approximated by a Boolean function, so even just a one hidden layer neural network, and usually when people talk about the number of layers in a network, they just refer to the number of hidden layers. So a single layer network, in some sense, can approximate anything if we make it big enough. But we have an even stronger result where with two hidden layers, any function can be approximated to arbitrary accuracy by a neural network with two hidden layers. It's sometimes called the universal function approximation theorem for neural networks. So neural networks are an extremely powerful thing for us to build on top of, because this one layer or this two-layer neural network, this basic module that we introduced today, that basic module can represent any function. So if we want to build more complicated models, well, it makes sense for that to be our building block, because it's kind of a nice, universal, differentiable building block. And what can this actually look like? Well, for example, you can think about what a neural network might have to do to, say, learn the identity function. And we won't go into too much detail here because we're running out of time, but you can actually train a neural network to learn to do this identity function. You can actually look at the weights on the hidden layer. It's kind of neat. You can kind of see, and it's not going to come to the same answer every single time. But you can see this neural network can learn all kinds of different ways to represent this identity function. This is a really simple Boolean function. This is just an example of the fact that these neural networks are really quite expressive. And one thing that I'll note that I didn't mention when we were talking about the gradient descent here is that, yes, these neural networks are very nice, differentiable, that's great, but they're totally non-convex. So if we remember when we were talking about linear regression, it was super nice because it's convex, which means that when we run gradient descent, we're always going to get the same answer. It's not true for neural networks. Neural networks are too complicated. There's no guarantees about what you converge to. So what this means is that how you run the gradient descent, how you initialize, what your learning rate is, all of this becomes way more important, because with linear regression, we can say, oh, well, we have the closed form. We know that our gradient descent should be able to do as well as the closed form solution. There's no closed form solution for neural networks. It's a bit of a, it's a bit crazy. We just have to try our best using gradient descent, but it's not always going to converge to the same thing. Me and you could run the same neural network, from the same tutorial, and just based on differences in our random number generator, or even just differences in how the GPU does non-deterministic computations, will come to different solutions. So this isn't that big of a deal, as we'll talk about as we go throughout the deep learning section. Despite the fact that they're not guaranteed to converge to anything reasonable, they really tend to converge to reasonable things almost all the time. But it is a challenge, say, for reproducibility. Is one example here that now we have these neural networks that, with SVMs, I run an SVM, you run an SVM, we get the same thing because the margin is uniquely defined. Not anymore. Neural networks can be all over the place. So now when we talk about how we can generalize neural networks, this is the last slide, and this is going to lead into tomorrow, not tomorrow, but Tuesday. So what we can do, today we talked about this classic neural network. We used these sigmoid activation functions. But in practice, we don't actually need to use sigmoids. In practice, we can have an arbitrary nonlinear activation function. I'll talk about some examples. So instead of using a sigmoid, we could use a tanh, a hyperbolic tangent, for example. We can throw anything we want for this activation function where we've been using a sigmoid. Historically, people use sigmoid because it was easy to take derivatives of by hand. But next lecture, we're going to introduce an automated thing to take derivatives for us, so we can start throwing in all kinds of crazy things. We can also make networks as deep as we want. We can add regularization of different types on different layers. We can do all kinds of things. Basically, we're going to transition from this world of us writing down a model and needing to derive the specific learning update rule to this world where we write down a model, we define this is what our hidden layers are going to be, this is our activation functions, this is our regularization, and then the derivatives are just computed for us. So this really frees us up to start thinking about really complicated, really crazy models. And so it's an important transition kind of conceptually in this course, because we're going from the case where it was really possible to solve by hand, what the solution was for this hard SVM on this AND case. And, it's possible to kind of write down the decision boundary for naive Bayes and these kind of things. We're going to transition away from that. The models are going to get a lot more complicated, but we're not going to have to take derivatives by hand. So the models get more complicated, and with the specification gets complicated, but the learning becomes a black box to us, which has positives and negatives that we'll talk about a lot over the next few weeks. So that's all for today, and I'll see you next week for backpropagation.